So in this video, I'm going to talk about the periods of the Carlitz module. Okay, so we're going to be considering the so let rho be a Drinfeld module over C. Again, C is the algebraic closure of 1 over T, and then we're going to take the algebraic closure, and then we're going to take the T-adic closure, T inverse adic. So we take the closure with respect to the degree of this thing. Okay, so we take a Drinfeld module over C. This is going to be the Carlitz module. So this means that rho T of Z is going to look like Z to the Q plus T times Z for Z and C, and the rigid analytic complex numbers. And then the claim is, the claim or lemma, I don't know, we should call this a proposition, is that the lattice of periods is going to be generated by here pi tilde of A subset of C. So we said that we already proved that they were an A module. Here A again is FQ of T, capital T. And let me say what pi tilde is. Pi tilde, where pi tilde, this is the Carlitz period, it's going to be equal to 1 over Q minus 1 times this infinite product. So this is where we're going to kind of do kind of like a classical, it looks really classical, 1 minus J over J plus 1 here. And then we recall that this J thing looks like T to the Q to the J minus T. Okay, so we're actually have this explicit transcendental number, right? In this kind of like that comes from the kernel. Okay, so remember that this whole thing is defined to be the kernel of the Carlitz exponential, and this is, we have this kind of explicit period here, and this is what we have, an explicit generator that you can write down using rigid analysis. Let me make some remarks. So first, the element 1 over Q minus 1. So this is T to the Q minus T over 1 over Q minus 1. So this can be pinned down by looking at the binomial theorem, and choosing roots in K infinity. So this is equal to FQ 1 over T. So you can actually like pick some roots. So if you factor some things out, you can pick some roots so that you pin down the actual element here. Okay, and then the other thing that I wanted to say, that this thing is called the Carlitz period. Okay. So that being said, how do we do this? So to do this, we'll need some version of the Weierstrass theorem. So there's kind of a theorem, and so this is kind of a factorization. Okay, so let f from C to C be entire, rigid analytic. Then, well, first, the zeros here So this is the set of z and c such that f of z is equal to 0. These are discrete. Okay, so they can be separated by balls. And the second thing is that, so that for every one of these entire functions, there exists an n, and there exists, so this is a natural number, and there exists a constant in the rigid analytic complex numbers such that the following holds, that f of z looks like, well, the constant times z to the power here, n, times this product, 1 minus z over ai, I is equal to, let's say, I is, where ai is not equal to 0. Okay, so here we can make these be all the roots. So, and ai is equal to z of f, occurring with multiplicity. Okay, so what this is saying is that every entire function looks like a constant times this thing times its times the this thing which makes it which makes these zeros appear. So like when we plug in ai, this is going to be 1, and this whole thing is 0. Okay, and so this is just this is just like in complex analysis. And what this really says is that an entire function is determined by the divisor, its divisor. And that's pretty much it. And so we're going to use this to look at the Carlitz exponential. Okay, and let me do that now. And so what do we want to say? Well, there's actually a theorem that says, so here's the theorem. So I'm not going to prove that theorem above, but I am going to say what happens when we use it. So, and so this is due to Carlitz. And it says the following. It says that, so if e is equal to the exponential for the Carlitz exponential, okay, then we have the following. It says that, that this, we have a certain product. It says, this is the product. Alpha in a not 0 of 1 minus z over alpha. Okay, so we have this product over all the polynomials here. And this is kind of this really cool formula, and it says that this thing is equal to this kind of modified Carlitz here, this Carlitz exponential. So we have this is the infinite product expansion for the Carlitz exponential. Okay, and so this uses, okay, so what does this thing use? It uses the rigid analytic Weierstrass preparation, rigid analytic Weierstrass factorization, and then it uses kind of some what I'll call is rigid calculus, and I'm not going to go over the details. So it's just some manipulations using these d factorial type things. So these dj's and things like that. Okay, so as a consequence of this, we get a formula for the Carlitz exponential again. So e is going to be the Carlitz exponential, and we have the following. It says that z is equal to, so the alpha in let's say pi tilde a of 1 minus z over alpha. So like this. So this minus 0 here is equal to the Carlitz exponential. So that's the formula that we get. And so how do we go from here to here? So the proof is you kind of make the substitution that w is equal to pi tilde z, and then you get this formula in w. Okay, and I think somewhere in here you have to use the fact that every entire non-constant rigid analytic function is surjective. So in these formulas, you are definitely, I mean, if you look at them, they're an infinite product. So it's kind of obvious that you're heavily using analysis in these things. All right. So so that's really all I wanted to say is kind of how these that's all I really wanted to say about periods in that example.